Okay, now we start over here. We do the same analysis for the second ramp where the ball starts at the 120 centimeter position and moves to the 0 centimeter position so that it's moving in the negative direction according to the way we set up our scale. And we want to find the equation of motion for that ball, assuming that it takes 6 seconds to get down the ramp. So, now I'm writing things out a little more formally here, but V2 of 0 is 0. V2 is going to be the velocity function for the second ball. And it starts from rest. Okay? Then x2 of 0 is 120 centimeters. Why? Because we said it starts at the 120 centimeter position at time 0. Okay? And then at the same, I think it was phrased, at the same time the first ball starts. But that was it, time t equals 0. So that's what we have. Then x2 at 6 seconds is going to be 0. Why? Because the ball's rolling down a 120 centimeter ramp that starts at the 120 centimeter position, okay, and goes in the negative direction, so it's going to go to the 0 centimeter position. So x2 of 6 seconds is going to be 0. Now, our average velocity then is our displacement, and that's our change in x. Now, that's why I wrote it before, and I wrote delta x then is negative 120 centimeters, and that is displacement, not distance, displacement. And velocity is always displacement divided by the time interval. So that's negative 120 centimeters over 6 seconds, or negative 20 centimeters per second, so we sketch our graph. Now, our graph goes out from 0 to 6 seconds, because that's a time interval for this motion. And the average at the midpoint is your negative 20 centimeter per second average velocity. Now again, similar triangle here and here, meaning that we have a rise here of negative 20 centimeters per second, so we'll have another negative 20 centimeters per second. Did I say 20 or 120? I think I said negative 20. Negative 20 centimeters per second here, giving us negative 40 centimeter per second rise from here all the way down to here, so that the velocity V2 at this point will be negative 40 centimeters per second. Now we easily calculate the slope. Rise is negative 40 centimeters, run is 6 seconds, and that comes out to negative 6.7 centimeters per second. Now that's what I used down here, but I don't think I wrote it here, so let's be clear. Okay? And then how do we get the area? Well, average graph altitude is negative 20 centimeters per second. Now that's not really an altitude, and you can't really have a negative area, so I'm kind of being a little fuzzy with the ideas of altitude and area. You can have a negative altitude, but you can't have a negative area. So what I'm calling the area, I'm still going to call it the area. I could call it the signed area or something else, but that's so clumsy that we just understand that you can have negative areas, okay? With graph trapezoids. Okay, so that's a negative graph area, if you like. We multiply the average velocity by the time interval, we get negative 120 centimeters, and we better get negative 120 centimeters because the average velocity multiplied by the time interval is your displacement, and that's negative 120 centimeters. So again, consistency check. Okay, so V2 of t equals what? Well, it's AT of the form AT plus B, where A is the slope, and the slope is negative 67 centimeters per second squared. Okay, and by considerations that we had before, when t is 0, V has to be 0. So if t is 0, this is 0, so we better not have anything else in this equation, or if we did, we might well have something that's not 0 at this point. Okay. So there's your V2 of t, easy to reason out. So your x2 of t, by the same reasoning we used before, is going to be negative 1/2 of this times t squared plus a constant. There's no bt term on your velocity, so you don't have to worry about that, although in general we will. Friday we will. Okay, so there's your x2 position function, but we don't know what c is yet. So let's see, x2 of 0, well, it's not 0 anymore, it's 120 centimeters, so you don't just automatically write down x of 0 equals 0. X of 0 is whatever the position is when the clock is at t equals 0. In this case, that's 120 centimeters. Also, of course, by this function, x2 of 0 is just c, the same way it was before, so c has to be 120 centimeters. And now we have two functions. We have x1 of t, x2 of t. And here they are. I don't have to read them to you. I mean, there's our 120 centimeters. That's our c. Here's the rest of it. So we have two position functions. I didn't take the time because we were kind of pressed for time. But if I graph these two quadratic functions, and you should know from pre-calculus how to graph quadratic functions, we haven't really talked about it, but one of them is like this, and one of them is like this. And one of them goes out to 4 seconds, and one of them goes out to 6 seconds. This one starts at the same position, because remember now this is position versus time, not velocity versus time. Same position, so really probably, it stops right there. And the position is the same where this one starts as where this one stops. And we've already looked at this kind of a graph, so I'm not going to say too much about that. So my question is then, what's the time when you have the same position? Now, it's a nice idea to visualize this on the graph. There's the time when the positions are the same, and here's the x when the positions are the same. We want to try to find those. Okay, well, I'm getting a little ahead of myself. We'll do this in another video, but that's one way we're going to be able to use these functions.